Record on cloud. Okay. That's what I'm looking for. And now, anyway, I hope everybody can see this. It's has anybody looked and seen the solutions on OneNote for this quiz? Anybody? It's a very odd feeling. You're looking, you saw them. Okay, Joel saw them. Anybody else? All right, Zachary. All right, I want to go through it though, because there were, and I'm going to say this. I'll make it up to you. A lot of people felt they didn't have sufficient time to complete this quiz. Maybe before I say anything more, I should say this. I had tested positive for COVID on Saturday. I had a fever, and I went in and Saturday morning to urgent care on South College before they were basically when they opened up and they tested me and they said you have COVID for 5 days. After that day, you have to remain away from people. Then you have to wear a mask for 5 days. So I won't be there until Friday, hopefully. I had the worst headache of my life. Well, one of the worst, at least on Saturday. I didn't have much of a fever. Sunday, the headache went away, had a little bit of a fever. Today, I don't have a fever. I'm a little stuffy, but overall, basically, I think it's over. I'm going to bet that there are several people in this class that have had COVID or have COVID, because just the numbers of things I'm getting from people, I haven't really checked who is that person that I get sent information about from the dean's office. But if you have COVID, hopefully you'll get over it quickly. And please do the quarantine that they recommend, because this thing, it's irritating right now more than it is lethal, but it's still dangerous for some people, especially those with pre-existing conditions. And as I was told, diabetes and high blood pressure. So anyway, that's just for everybody's edification. So I wanted to go through this. And I assume you can see what I have before me. Is that right? That's the quiz. So the first part for this quiz, they both had the same questions asked, only in different order, was I give you region 1 has constitutive parameters, epsilon equals 72. Man, I don't know if you can see that or not. Let me see if I can increase the size a little. All right, can you see this okay? Okay. By the way, if you can't or anything like that, just who can see your messages recording on? Is that a question to me? Well, anyway, I believe the recording is on. At least it says it's on. And the messages are in the chat window. I hope you can see this. I haven't used this in a long time, but hopefully we can just get through this week and be done with it. Anyway, let me get on to this. So they give you constitutive parameters, and then they give you an E field at 300 megahertz. And the first thing I want is the propagation constant. So this is one that's neither good conductor nor perfect dielectric or anything like that. So you put J omega mu sigma plus J omega epsilon, and you get this answer right here. That was nothing more than a plug and chug, but you can make mistakes oftentimes with the square roots, or sometimes you forget omega is 2 pi f. It's always possible. Next thing is determine eta. That's the simply the intrinsic impedance, and that's the square root of J omega mu over sigma plus J omega epsilon. That's that. And the last thing is determine the phasor form of H. Well, H, of course, is 1 over eta, unit vector in the direction of propagation cross E. I say that it's propagating in the Z direction, so the unit vector in the direction of propagation is AZ. And the next thing is it's 1 over eta, and I didn't show you this, but should be 1 over magnitude of eta, and take the angle up here when all is said and done. And I don't see that here. There should be an angle here also. There should be e to the minus j angle associated with eta, and let me see if I can get that. Wait, now this is, you've heard me mention MathCAD, right? All right, this is MathCAD, if I can get it right here. So MathCAD is what my preferred thing to use to do simple stuff. And if I want the angle, I'm going to just do this real quick. So I have epsilon relative equals 72. Mu relative equal 1. Epsilon equal 8.854 times 10 to the minus 12. Mu naught equal 4 times pi times 10 to the minus 7th. And sigma equal 5. F is 3 times 10 to the 8th. Omega is 2 times pi times F. Finally, might as well do the whole 9 yards. Gamma is equal to the square root of 1j times omega times, it's just mu naught in this case, times sigma plus 1j times omega times epsilon relative times epsilon naught. So you get that, and F then for eta. Can you all see this, what I'm doing here? Okay, John, right, Karen? Zach? I mean, some people, I've learned this lesson, they just start listening and tune out because they got the solution. I'm trying to make sure you see this. By the way, you will never regret using MathCAD. You can get the free version, it doesn't do everything, or you can use the engineering version, and it does everything. This is my favorite little tool because it's what you see is what you get. And I'll show you a few other things about this little joy, this tool right here that I find very, very beneficial. Trying to move this stuff around. All right, so eta is equal to, eta is equal to square root of 1j times omega times mu naught over, over sigma plus 1j times omega times epsilon relative times epsilon naught. I'm going to get in terms of real and imaginary, but I'll take magnitude of eta and then angle. Oh, never mind. I forgot. This one uses argument. And I want it in degrees. So it's 38.24 degrees there. Now, that means when I come over here, for this answer right here, there should be, that angle right there should be 32.8, minus 32.84 degrees. Really, it should be in radians, but I'm just doing this for everybody's benefit. So you can see, can you all see that okay? That's a very odd feeling. That's okay. At least we're getting through it somehow. Next, let's see. The next is I got a 500 megahertz plane wave traveling in air with, this is the average power density. And I want to know an electric field. I want to know the magnitude of the electric and magnetic field. All right, the first thing you hear is air. That means eta is just equal to 120 pi ohms. Then after that, because power density, P av, is equal to 1/2 magnitude of the E field squared over eta. 2 times P av times eta, square root of that is equal to the E field. So this is actually equal to the square root of 2 eta times average power density. And that should be correct. It shouldn't cause anybody any problem. Can you all follow me on this? The answers are there. I mean, can you all see this? Okay, Zach. I'm trying to get a read. Is it okay, Sydney? Thank you. I'm just trying to make sure that you can see this. The same. How do I get H? Simply take the magnitude of the E field by eta naught. That's it. So that's going to be this. Most people got that right. I mean, the grading, I'm not quite finished. There are a bunch of perfect papers, but there are a bunch of people that somehow got confused. And this is the part with the most confusion. So I want to talk about this. This is the last part. Let me try to blow that up a little more still. Hopefully you can see this. Okay. So a lot of people were confused on this. So assuming free, it says assuming free space, this is the E field. And I wanted to know, AP, that's the unit vector in the direction of propagation. The way you always get the unit vector in the direction of propagation is you look at the exponential term with the J in it, and you first see what the variable is. If it's Z, it's going to either be plus and minus Z direction. If it's got a minus J beta Z, it's going in the plus Z direction. So this is actually plus AZ. Then it asked for the H field. Well, because it's in free space, to get the H field, I know the magnitude will be E divided by eta naught, which is 120 pi. I can put that here just to make sure. 120 pi ohms. And after that, the only thing you have to do is put E to the minus J 40Z. That's the same here. And you remember that E crossed H is the direction of propagation. Well, E is in the AX direction. Crossed whatever H is has to be in the AZ. We can get it another way, but that's probably the easiest. So EAX crossed something equals AZ. It has to be AY. Right there, AY direction. How many understand that? I mean, it's some way, if you're listening. What? You can't see what I see, but I see no faces. I got some thumbs. I got 3 thumbs. Thank you very much. Maybe 4 thumbs. Oh, and a hand. I see. This is interesting. All right. I'm trying to make sure I can communicate to you. And I'm not going to even do a head count. I don't need to. So that's basically the way you get it. To get the frequency, remember this is beta 45, right? So to get the frequency, I'm just going to pull this up for a second. If you want, remember that in general, gamma is equal to alpha plus J beta. That's equal to the square root of J omega mu times sigma plus J omega epsilon. But if it's lossless and sigma 0, this is just equal to J beta is equal to gamma, and it's equal to simply J omega. That would be J omega times J omega, because there is no sigma now, squared, square root of that is J omega times square root of mu epsilon. And that is simply equal to J omega. Well, square root of mu epsilon is square root of mu naught over epsilon, or times epsilon naught times square root of mu relative epsilon relative. Well, the square root of mu naught epsilon naught is simply C. So this is J times omega over C. And then it's the square root of mu relative epsilon relative. Now this is free space, or it's air. So these terms go away, which means beta in magnitude is omega over C. Or you can say that really beta times C is equal to omega, which is equal to 2 pi f, or the frequency itself is beta times C, the velocity of light in a vacuum, divided by 2 pi. And for this one, does everybody follow me on this? If you do hand anything, okay, good. If you do, it's important you do, because this was not meant to be a long, this is supposedly about an 8 to 10 minute quiz. And I'm not sure where you got stuck in the weeds on this one, but so this is how you get this frequency very quickly. Only thing you have to do is take beta times c, which is 3 times 10 to the 8th over 2 pi. And I assume you know 3 times 10 to the 8th is the speed of light, but if you didn't, I will provide that information. You should really know that. And that's the easy way to get this anytime you have a vacuum. So the next one, does anybody have any question about this problem, by the way? You can unmute yourself if you want. Oh, if you asked who can see your messages, I can see them, and I think the class can see them. And the recording is on. I think that's enough. Okay. Now, for this one, if you look here, it's the H field, right? Now, listen, the way I got this H field is just magnitude. If I wanted to get the H field using the other technique, it would be simply 1 over eta, unit vector in the direction of propagation, cross E. You all see that right there? You can do that too. Either one will work. Here, I give you the H field. And the first thing I want is direction of propagation. So you look at the exponential term. It's got J30. I hope you can see that. Sometimes I'm not sure. Can you all see it? If you can't see something, just let me know. So for this one, you got J30Y. You know it's in either plus or minus Y. Because it's got a plus J30Y, it's in the minus Y direction. Then to get the E field, you can use simply the equation, since they want E, it would be equal to minus eta, unit vector in the direction of propagation, crossed into the H field. You can do it that way if you want. That'll work. As a matter of fact, if you do it that way, then you would get eta, or 120 pi, times minus AY crossed in to the H field, which is 10 times e to the J30Y AZ. It would result in this. And it has to be perpendicular to the direction of propagation, the field orientation, and the H field, and it's in the AX direction. And to get the frequency, again, you take just beta 30 by times c, divided by 2 pi, and you get the frequency right there. Now, if you think about this, if you knew that ahead of time and you felt comfortable with it, these are not very quick or very time-consuming calculations. They're fairly fast. But if you're struggling and unsure, you can get really wrapped up going back and forth with different equations for beta and wondering. Key thing, again, is free space. Finally, for the H field here equals 20 times e to the minus j 45 z ax. Here, the direction of propagation is az, and I think everybody can see that because it's e to the minus j 45 z. Since it's minus j 45 z, we know it's in the z direction and it's going in the positive az because that's a minus j there. And to get the E field again, we could get the E field using minus eta, unit vector in the direction of propagation, and then crossed into the H field, 20 times e to the minus j 45 z and the AX direction. And this would result, to get the frequency, by the way, this frequency has to be the same as the first one because they both have e to the j45 in free space, and it's 2.149. This is the area of the quiz that most people struggled with, and I think it was because they were unsure about how to get both direction of propagation and the actual and the frequency from beta. But I hope this answered that, and the solutions are up there. Do you have any questions about this before I go on? Okay. All right. Well, that's that. Any questions at all? There were the same questions in different orders on both quizzes, so there's nothing that should be that I didn't cover. All right. So that's that. Now, let's get a different thing. So now, what I wanted to do is just pick up where I left off, but I'm going to use the book, if you don't mind, as a reference. Yeah, go ahead, Ben. You can unmute yourself. I think you can at least. Can you hear me, Ben?
Hey, yeah, I can hear you. It wouldn't let me unmute. I was asking, does beta need to be in radians?
Well, beta is radians per meter, right?
Right. I thought so. It's not in degrees then.
No, well, it theoretically could be. Beta almost always is in radians per meter. If you're going to use that, like the calculation of alpha plus J beta with the fundamental form, alpha is in Napier's per meter and beta is radians per meter.
Okay, so it was 45 radians per meter?
Yeah.
Okay.
And times Z is meters.
Okay. Okay, thank you. That makes sense.
Sure. By the way, I think I let everybody unmute themselves, but if you want to ask a question and can't unmute, just stick up your hand. I thought I did that at least. Maybe I didn't. Did you have another question?
No, I didn't. That was it. Thank you.
Okay, your hand's still up. That's the only reason I said that.
Oh.
But may not even know that. That's okay. All right, let me try this. So let me, what I really wanted to do is, you have to bear with me on this one. I was trying to get through first of all, are there any questions at all about the homework? I gave you just the standard normally incidence problems, several of them, and I was curious if you had any questions at all. They're very straightforward. They're simple problems. And this is section 6-7. So did you have any questions at all about these? We should do at least one. I'm going to try to, how can I get you guys to unmute? Let's see. If you do, put up your hand and I'll try to allow you to. If I need to unmute you, I will. Okay, hang on for 1 second. Wait a second. Jacob, were you there? You were there a second ago. Now I don't know what happened to you. If you got a question, put up your hand. And if I don't see it, type something in the chat and I'll try to get you. I'm just looking for it. I thought Jacob had a question, but I might be wrong. Anybody have a question about the homework at all? So here's a question for you. How many did the homework? How many tried the homework? Well, you're honest. I'm getting no response. It doesn't tell me anything, but okay, Thomas, you did. Good for you. John Ray, you did. Okay. And D, you did good. I mean, 8 questions at all? It's very rare for no questions, but I mean, if the professor's sick, I understand. We need to do one. Do you guys got one you want to do? I tried. Hold on. Who is this? Let me get this one. Could we do 640? Yes, I tried, but it didn't seem to want to. Who is this? Is this Jacob? Okay, where are you? Looking for you. Where are you? I'm trying to stretch this screen so I can see everybody. Jacob, I don't even see you. If you're still there. All right. All right, we can do 640. I think that's what somebody asked. So 640. It says UPW wave in a lossless magnetic media. So here's the parameters for this one. I hope you can see it. This is problem 640. Second. Epsilon relative for this one equals 16. For z less than 0. For z less than 0. And they give you an E field equal to 10 cosine omega t minus beta 1 z ax plus 20 cosine omega t minus beta 1 z plus, oh boy, let me do it this way, plus 20 times cosine omega t minus beta 1 z plus pi over 3 a y volts per meter. I'm just restating the problem. And they say is incident on a lossless media characterized by, so what they got is this. This is Z, and this is the origin 0. Down here you got epsilon relative equal to 16. And up here, this is a weird one. Mu relative, this looks like a Wentworth problem. Up here, call this region 1. In region 2, you have mu relative equal to 12 and epsilon relative equal to 6. Find the instantaneous expressions for the reflected and transmitted electric field. All right, for this problem, the key thing is to find the intrinsic impedance in region 1, so I'll call it A to 1, and the intrinsic impedance in region 2. Now, y'all follow me on this one? That's the only thing we need to do. And if you look at this, for A to 1, it's really, since they're both lossless, do you agree with this? Sigma is 0 in both cases? All right, if sigma is 0, then A to 1 is just equal to the square root of really mu over epsilon, right? Because sigma is 0, so the j omega is canceled. Do you all follow me? And that is simply equal to the square root of mu naught over epsilon naught times the square root of really mu relative, which is 1. This is in region 1 over epsilon relative, which is 16. So that's going to be simply 120 pi by 4, right? Square root of 16 is 4. And that's simply 30 pi ohms. Do y'all agree with that, first of all? At least y'all see what I'm doing? Okay, good. Sydney. Yeah, I'm assuming you do, but if you don't, please just let me know, Zach. The next one for eta 2, this is a little bit different. It's still lossless, so it's square root of mu over epsilon. Now it's going to be equal to square root of mu naught over epsilon naught, right? And then it's times square root of mu relative. In this case, for region 2, it's 12 over epsilon relative, which is 6. Those are weird numbers for him. So that's 120 pi. That's this number. And then it's times the square root of 12 over 6, or square root of 2. That can't be right. He's got a mu relative of 12. Wow. So it's a magnetic material. So it's square root of 2. Now, once we get that, we get the reflection and the actual transmission coefficient. The reflection coefficient in the region is eta 2 minus eta 1 over eta 2 plus eta 1. And that, if you look at this, since 120 pi is in both of them, I'll do it just the normal way. So eta 2 is going to be 120 pi times square root of 2. And it's going to be that minus eta 1, which is minus 30 pi over 120 pi square root of 2 plus 30 pi. And that should, as it's going to be strict real, I can do that. I'm going to do it with MathCAD so you can get an appreciation for this thing. So for this one, I'm going to just put eta naught equals 120 times pi. And then eta 1 equals 120. Really eta naught over 4. And eta 2. So gamma that's what I get for gamma. And for tau, you can get tau 2 ways. You can add 1 to that, or you can just say it's 2 times eta 2 over eta 2, sorry, plus eta 1, 1.7. Yeah, all right. And what else does it ask for? Okay, so for the reflected and transmitted field, the only thing I need to do, and I hope everybody can see this once I get it up here. The only thing I need to do is this. I take this value here. This is the incident field. For the reflected field, what's going to change is it's going to be minus here goes to plus, minus here goes to plus. Do y'all follow me on that, class? I mean, Jacob, you asked this question. I don't see you here, but you're probably amongst this soup I'm looking at. Sydney, you see it. Okay. So this will, for the reflected field, this will become plus, this will become plus. I'm going to write that down there. And instead of 10, it's going to be the reflection coefficient. And the reflection coefficient was what? I didn't write it down, but I'll get it here. I think it's 0.7, right? 0.7 times the incident field. So it'd be 7, and it would be cosine of omega t plus beta 1 z. It'd still be in the AX direction. And then you would get plus, so then it's going to be plus 14. So it's 0.7 times 20 times cosine of omega t plus beta 1 z plus that phase constant of pi over 3, and it would be AY. Now that's the reflected field, the transmitted electric field. Then you get the transmission coefficient, which is 1.7 times 10, which is going to be 17 cosine of omega t. Does he give us the value for frequency on this problem? No. So if he doesn't give you frequency, you don't need to mess with omega and beta changes, but they would, the omega will never change, beta will. So that's going to be minus beta 1 ZAX, and then it's going to be plus, and this is going to be 34, because it's 1.7 times 20 times cosine of omega t minus beta 1 Z plus pi over 3 AY. All right. Did that answer your question? Where are you? Oh, there you are, Jacob. I'm sorry. Here, I can unmute you. Did that answer? Okay.
Yes, sir. Can you hear me?
Yeah, I can now. And I don't know why this thing isn't unmuting, because I thought I let it anybody to unmute themselves, but maybe I didn't. Does anybody else have a question about this problem? It's a little awkward. Wentworth, I mean, this is something where they've got really, he calls it a UP, what is it, UPC wave or something like that, UPW. It's uniformly polarized wave. It's standard cosine variational frequency and lossless media. So it's really just getting familiar with some of the ways we bookkeep this thing or keep track of it. Does everybody follow me on this, class? Yes, hold it, Finley. Let me get you. Go ahead.
Would we use beta 2 for the transmitted field?
Absolutely. I'm sorry. The problem is you're absolutely right. This should be beta 2. He didn't give us a frequency, so we can't really get beta 1, but you're absolutely right. It should be beta 2, and beta 2 will be different from beta 1. Does that answer your question? Hold on. Okay. All right. So I want to say one other thing. He did not give us omega. If he gave us omega, we could calculate beta very easily, all right? Because it's lossless. So beta is just going to be equal to really omega times the square root of mu epsilon. And it's really omega c. Okay, Finley, hold on. Go ahead.
Sorry, I forgot to lower my hand. Sorry.
That's all right. I mean, if you got a question, just let me know. But the real thing is, if he gives us omega, we can get beta. Beta is omega times square root of mu epsilon. If you remember that, you got it for losses. All right, D, you got a question. Hold on. Go ahead. Okay.
On the math CAD, when we calculated gamma, I think you put the denominator reverse in 1 plus n2.
Well, it doesn't matter the order because they're additive. You can add n2 plus n1 or n1 plus n2.
Okay. That was it.
This part has to be right. It has to, the impedance you're going into minus the impedance you come from. But I'll tell you one thing, I'm just pitching this. This stuff, MathCAD, is fantastic. Now, here's why. Suppose, just out of curiosity, instead of making 8 120 pi, and I'm going to change it everywhere. I make it 120. Everywhere it changes. That quick. If I make this instead of 4, make it 2. everywhere it changes instantly. So if you got equations with all sorts of stuff dependent on variables at the top, I can change one thing and everything changes right away. Did you have another question, Dee? Did you have another question?
Oh no, sorry, I didn't see
Okay.
anything.
Yeah, if you can lower your hand, I know it's a pain, but it's the only way this thing works. So anyway, I hope that answered your question about this one. Does anybody have any other questions about the homework before I continue? I must say, I was so glad we were done with this, and I'm sorry I'm the one that caused it to come back, but such is the life we live. So now what I'd like to do, I'm not going to go through all the calculations the way I would normally do it on the board. I just want to bring you up to speed. We were talking about, any other questions before I continue? Okay, I wanted to talk about oblique incidence, and there's both TE and TM. So I am going to bring back that camera. And I'm going to probably, yeah, I think, hopefully, let me get that autofocus on just for a second. All right. Can you see the cursor on the screen that I'm moving right now, class? Can anybody help me? I've got a cursor. I can see it. I don't know if you can. That's moving across. You can? Okay. Thank you. Thank you. If you look at this, remember I was telling you about the Z prime. It's neither in the X or Y. It's in both. So Z prime is actually equal to this. X, let me blow it up a little. X sine, this is on what page in your book? Page 360. It's equal to X sine theta incident plus Z cosine theta incident. There's theta incident. These are the two different materials. It's in the Z direction and X direction. It's propagating. This is TE. So the electric field is perpendicular to the plane of polarization. It's really in the plane of the separation plane. It's completely immersed in that when it goes through, or normal. It's really parallel to it there. So the H field, of course, you get by taking 1 over eta. The E field, 1 over eta, unit vector in the direction of propagation, crossed in to the actual the H field you get by taking 1 over eta, unit vector in the direction of propagation, crossed into the E field. When you do that, you get this. I think I did that last time. Do you remember if I did or not? Anybody? At all? I know I was working to it. I think I got that out of the way before your quiz, or not? No? Anybody remember me doing it? New message. Hold on, I got a new message. Yes, you did. Thank you. That helped. All right. I think you did. It's honest. All right. Anyway, when you do that, they're really going to be an incident electric field, a transmitted and a reflected electric field. That's what this stuff is. This is the incident electric field and the incident magnetic field. And we get them the same way we did everything else. Then the next thing, you got to get the incident transmitted field, or reflected field in this case. Incident reflected field right here, and the transmitted reflected field. Now, I'm not going to go through the proof because I like the board for that. There's a lot of stuff, but really it's straightforward. You get a unit vector and direction of propagation. Once you have that, it's just a bunch of cross products to get the rest. So I got E reflected, H reflected. The one thing about this one is Wentworth's book leaves the minus J beta 1 here, and he allows the minus sign in the Z direction to appear here. So it's propagating the plus X direction and minus Z direction. It's weighed by a cosine in the Z direction and a sine in the X. Finally, the transmitted field has this, it looks the exact same way as the incident field, only instead of having the angle here being incident, it's transmitted. Instead of beta 1, it's beta 2. Now, I'll tell you, that's it's important to know that, but here's really why all this stuff's so important. And this I will mention in a little more detail. You all realize that's a lot of time on mathematics, but it's going somewhere. It's not for nothing. So when we think about the boundary conditions, remember how we did this for the normal incident waveform. The way we got reflection and transmission coefficient is we equated the tangent electric field on one side to the tangent electric field on the other, and the actual tangent magnetic field on one side to the tangent magnetic field on the other. Are you with me on this, class? All right, when we do that, what that means is the tangent E field, the E field itself is completely tangent. It only has a perpendicular component, a Y component that's exactly parallel, or it's right in the plane of the two conductors or the two different media. So the E field on one side is the incident field, e to the minus j to beta 1 x times theta incident. Let me see if I can blow that up. So I'm going to make a point here, and I don't want to have to rewrite the whole thing. That's this right here. That's the incident E field at the boundary at z equals 0. We're looking right at the boundary at z equals 0. This is the reflected electric field at that boundary. And this is the transmitted field. So E tan in region 1 is this. The tangent electric field in region 2 is this. They have to be the same. Can you all follow me? I know I'm almost out of time. Can you give me a show of hands if you did? Okay, thank you, Sydney. Anybody else? Anybody else? Okay, now here's the point. This is an extremely important point, and it's a lot of physics came forth from this. Now, take a good look at this. You see how each one of these terms has an exponential that's a function of a position vector x, or position, I should say. The only possible way this can be true is if all these exponential terms change at the same rate. You all follow me? If they didn't, this could never be true, except at one point. But this is true over the entire boundary for all x. So what that means is this, and this is so important, that beta 1x sine of theta incident has got to be equal to beta 1x sine of theta reflected, that's here, has got to be equal to beta 2x sine of theta transmitted. I'm almost finished. You all follow me on that? Why is that important? Well, we can get rid of x on each one of these points. And we see that beta 1 sine theta incident is beta 1 sine theta reflected. It means the incident and reflected angle are the same. So it says the angle it strikes on the incident side is the angle it's reflected off of on the incident side. And also we get beta 1 times sine of theta incident is beta 2 sine of theta transmit, or we get this. And this is called Snell's law of refraction. And I would highlight that. That tells me what the angle of transmission will be, regardless if the incident waveform is TE or TM. Can anybody follow me on that? Just give me a show of hands. I'll leave you go in a second. All right, I don't have any idea how many people are on, but I appreciate you being here. Now, I'm going to give you some simple homework on this one. I don't want to make it rough. Did you have a question, Ben? Or you just, boy, I hate to. I'll have this figured out by Wednesday. All right, I'm going to tell you this much. That is extremely important. Last question, then we're gone. How many have heard of Snell's law before? One? Well, whether you know it or not, y'all have. You've been in physics. Thank you very much. No, no, I never heard of it. That's a lie. Anyway, you should have heard of it. It's a very important law, and we're going to go through this. We're going to go through a bunch of other stuff that'll hopefully make sense of a lot of things that you've heard about in piecemeal and didn't understand why. Okay, so technically class is over, but I'll hang around. Do you have any questions for me? Anything at all? And I'm more than willing to answer questions. I may not be in the best physical shape, but I'll try my best. No? Well, it's been real, guys. I wish I could say more. It's very fun to see this. All right, hold on. Go ahead.
Hey,
Did you have-
will there still be a quiz on Friday?
Oh, God. Let me think about it on Wednesday. You're going way ahead of me. I'm just trying to get through today. But I understand your concern. Did you understand today, though?
Yeah, for the most part, I think so. Yeah.
You could understand the way I'm teaching them?
Yeah. Yeah, I understand it.
Okay, well, I mean, see, this is awkward to me. Zach, thank you. I will feel better. Logan, did you have a question? Yes, not. All right, hold on. I tell you, this is a weird feeling, guys. I see no faces and a whole lot of names and hands. But I hope you got something out of it. If you got any comments, just let me know. I'll hang around for a few minutes if you need anything. John Ray, did you record this too or not? You there? Go ahead.
I was looking for a way as well as I saw the report here. I have the ability to, but when you mentioned you did,
Yeah, I did. I'm going to have to see here. How do I get this recording out of this thing?
on Wednesday I can see, I can get in here early if
I mean, but I can give you permission to record.
Yeah, yeah.
Hey, you know, I don't know. I didn't want to ask this, but I bet you a lot of that people in our class have. I know at least one other person that does. There's probably several. So it's in a way, it's probably better we're doing this time so people can get over it.
Yeah.
And I'm pretty sure I got it in that class, but just because of the numbers of people in that class that have it, that I've been getting messages about. So it's packed like sardines, and I wish it wasn't.
Yeah, for sure. All right, well, thank you.
Yeah. Sydney, did you have a question? Just making sure. No? Brian? I don't know. Are you still there, City? I'm making sure. Any questions at all? I'll take them. If you want me to do another problem, I'll do it. Oh my goodness. If a camera is on, at least I know what's going on. Are you still there, Sydney? Right? Go ahead. You can say something, Sydney. Are you on? Oh my goodness. Okay. All right, guys. Well, see you Wednesday. Thank you.